Alright, so now let's look at problem number 2. And this problem is a situation where you have a pump driving a virus solution at the night at one condition and in the daytime at another condition, whereas at night the flow rate is 50 times faster than during the day, and for some reason the virus is inactive after it's been pumped at night compared to the day. And what is key is that it says that the virus is unstable at high shear stresses and after rapid mixing. So we got to use these two. We know these two facts and try to figure out some possible explanations for the variability in the virus activity. So first of all, let's think about it's unstable at high shear stresses. So this is flow through a pipe, and with flow through a pipe, we kind of just did it in the first problem, but also we've seen it in the class before where the shear stress is equal to negative delta P divided by 2L times R. And we know that Pusuli flow Q is equal to this equation right here. So we can rearrange this equation to find delta P over L. So we have the relationship for delta P over L, and we're able to then plug it over here in the shear stress equation to get our shear stress in terms of flow rate for pipe flow. So I would have expected you to definitely have this on your equation sheet because I gave it in a PowerPoint slide in class, and this one you could have used from the last problem, or I would expect these kind of things for the general pipe flow, channel flow, things like that to be on your equation sheet so you don't have to derive it again, even though it's probably take you 2 or 3 minutes to derive it, but still have these known equations for these simplified conditions on your equation sheet to make it a little bit easier for yourself. So now we can figure out the shear stress at the wall of R equals big R would be equal to this equation right here. So if we look at our night conditions versus our day condition, our night we have a flow rate of 10 centimeters cubed per second, and during the day it's 0.2. So we can calculate what the shear stress is at night. You get negative 8,150 dynes per square centimeter, and during the day you get negative 163 dynes per square centimeter. So you can see a very big difference in the shear stresses, and this shear stress is just much higher than during the day. The high shear stresses at night could inactivate the virus. So that's one explanation. Now the second explanation, we want to think about what could cause rapid mixing. So rapid mixing could be caused by turbulent flow. So to check with this, to check to see if it's turbulent or laminar flow, let's look at the Reynolds number. So again, the Reynolds number, when it's above 4,000, you're going to have turbulent flow, and you're going to have a lot of rapid mixing going on in the pipe. And Reynolds number less than 2100, you're not going to have any mixing. The flow is going to be laminar, and the velocity profile is going to be one in which your velocity is going to be kind of layered. So the Reynolds number is rho times the characteristic length times your velocity divided by your viscosity. So again, your characteristic length in pipe flow is going to be the diameter of your pipe, so we can plug in D for your diameter. Your velocity is just going to be your flow rate divided by your cross-sectional area. So for the day it's 101.9. So we can go ahead and calculate the Reynolds number here in the day. We find out that it's 509, which is less than 2100, so it's laminar flow. And at nighttime we see that our velocity is 5,095, and the Reynolds number therefore is 25,465, which is turbulent. So the turbulent flow at night is causing rapid mixing and could inactivate the virus. So those are the two things that I was looking for in problem 2 to find out of what could be causing a problem with the virus. Both the flow is turbulent and you're having very high shear stresses.